Unmute and mute these people so that they know each other. And theoretically, you think we're back on the road here. All right. So let's see. Got 2 people. I'll wait a couple minutes and see if more of them are going to appear. There were something like 8 before, I think. All right. All right, back up to 5. They're coming. So this is homework, what I'm showing you. I was very happy with it, so I'm going to make you do it as homework. It's one of these cryptographic attacks that is not too baffling. And the guy that wrote the blog on which I based this stuff said this should make you very, very afraid. All right, that's it. So this is Project 14. And here's the background. All right. Remember, we talked about cipher block chaining, right? If you don't use cipher block chaining and use electronic code book, then the penguin stays a penguin, and you can still see things, so that's no good. So this is the alternative. You add an IV to the first block, and then you take the ciphertext and use that as the IV for the next block. And the ciphertext here is used over there, so even if all the input blocks are the same, the output blocks will vary randomly. So that sounds pretty good, but take a look at what you've done here. You've got an XOR operation. Oh, it's not obvious in the encryption side. That's the encryption side. All right, so now suppose you want to encrypt a message that is not filling the box. It's only 47 bytes. So now you don't have enough bytes to fill up the last block, and you can't run the operation without a full block. You've got to put something in there, so that purple square has to have padding. Okay, you got to pad it to make it longer. Now, there are different ways to pad. You could just pad with zeros or whatever you want, but the one common technique is that you use this PKCS number 7. But here's, by the way, what we're going to focus on decryption, not encryption. And decryption has something pretty terrifying. Notice that you encrypt the first block with the IV, you get the result here, and when you take the ciphertext and you XOR it here to put it there. This is nothing in this path from the ciphertext into the last stage into the new plain text, which I'll follow with the mouse up here. If you follow this path from this ciphertext to the plain text, the only thing that's done is an XOR. And that is the weak spot that we're going to exploit. Even if you don't know the key and you don't know the IV and you can't do the encryption or the decryption, you can take ciphertext and mess with it in a way to control the plain text because of the cipher block chaining. So we're not going to find the key and we're not going to get in the message, but we're going to take good ciphertext and modify it to decrypt into any garbage you want. It's bloody awesome. So consider this. This is your 47 block. So you do this for your 47 byte message. It puts in padding and encrypts it to make 48 bytes of ciphertext. When you decrypt the 48 bytes of ciphertext, the last bit here will be your padding. Now, here's how PKCS number 7 padding works. If you need 1 byte of padding, use 01. If you need 2 bytes, use 0202. And if you need 3, you use 030303, and on you go. That's how it works. So that means if I modify this ciphertext right here, just that byte, that will, of course, ruin this whole block of plain text, because the decryption will scramble it all together. So I'll have some collateral damage. But the part I want is it will only change this byte of the plain text in the next block, because that ciphertext is used with no alteration as an XOR right here. So if I change that byte, it's going to change this byte by just XORing with a different result. So now I can modify the decrypted text here. I can control this byte precisely at the cost of completely scrambling up those 16 bytes in there. And the reason, of course, why this is a problem is because there's a whole lot of encryption used on the web. And on the web, you typically have something like a string of parameters in the URL. You've got yahoo.com, $ID equals name, P equals password, dollar amount equals 1 million. You have a whole series of parameters, and it's often okay to mess up some of the parameters to get control of one that comes later in the string. In fact, you can often even repeat a parameter later in the string, and it will be accepted. So you can make up for the ones you messed up. So this might seem crazy, but it's actually quite powerful to control part of the decrypted text. So let's just play. I just want to demonstrate this property in Python. I can change that byte, and it will only change this byte and mess up that red one. So we start Python. Here's some initial values. So here's my Python. I just set it up. I import AES. I give it a key and an IV. I just put in any random junk. I set it up for cipher block chaining, and I made a input sentence that's 47 bytes long. So now to pad it, I've got to add a character 1 to the end, because I'm doing this PKS number 7. So when I pad with 1 byte, I put in a 1. And now I could encrypt that. And that ciphertext is now there. This ciphertext is going to be the encrypted version of 48 bytes, where I added a 1 to the end. And now if I want to modify it, I can take the first 31 bytes, add the character 255, just run modification, and then this. And so now I've created, okay, this creates good ciphertext, which will decrypt to the real message. This creates modified ciphertext with 1 byte changed, okay? All I got to do is decrypt them. So let's take a look at them. All right, here's the raw input. What happened here? Oh, I'm missing a P in my print. All right. So this is the encoded ciphertext, and I'm going to make my screen wide. This is 3 blocks of 16. All right. And then I'm going to print mod encode of hex. Guess I got to get it from here. All right. There, this is what I want to show you. This is the original ciphertext. This is the modified ciphertext. You can see it's exactly identical up to, I'm losing my mind. It should be looking like this here. I should see a difference in the middle. And what have I done?
5685, and then, yeah.
It looks like it's exactly identical all the way. I must have done something wrong.
No, I see. No, it's not.
You see it? 503, double what?
Double F on the bottom. That's
yeah, this is the this is just the mod encode. Right, I need to do cipher decrypt mod encode. That's the problem. I'm looking at the mod, but I want to look at the decrypt. Okay, let me view the decrypted text. I'm catching on. Okay, the point of this is just so you can see the mod. I'm with you. And I only modified 1 byte, that byte. Okay, good. I'm glad you people are on me. So all I did was, this is the valid ciphertext with 5C, and I changed 1 byte to FF and leave it alone. Now I want to decrypt both of them. And that's what this does. This will decrypt the original ciphertext and then decrypt the modified ciphertext so I can compare them. All right. Now the first byte is the same. The first block is the same. And the second block is all destroyed. And the third block starts here, and the last byte is different. So the only bytes that are different are the whole middle block, because any change in that block will ruin the whole block, and the last 1 byte has gone from 01 to A2. So all this stuff will remain the way it is, but I control the last byte. Okay? All right. Now, this is just the facts of the system, and none of this is necessarily a problem. The problem is the padding oracle. See, the mathematics of AES and every cipher system is designed to handle a situation where you only know certain information. And the only thing the attacker is supposed to be able to see is the ciphertext. And if they can see a bunch of ciphertext going by and hunt through it for patterns, they're never going to find any, because that's what it was designed to prevent. But if you allow the attacker to gain some other information, it can ruin the whole thing. And the reason why the guy said this is terrifying is all you have to do is leak out whether the padding was valid, and that ruins everything. That's what makes it a padding oracle. So here's a vulnerable system. I make a function here. I'm going to call this pador.py. I've got it. I'll just bring it here. If I go here, let me go to the same directory, which is box website 141 projects. Okay, now, all right, here's my padding oracle vulnerable system. And this imitates a system that has been quite popular. All you do, you have some system that does AES encryption in CBC, and then when you decrypt it, you check to see if the padding is valid. And then you print out a padding error message if it's not valid. This is something a person might reasonably do. Rather than just saying invalid input, you would happen to say padding input to help your developer make it better, and then you might leave it that way in the final product because it seems harmless. But it's not. So let's play with that. You do it this way. You import pad_or. And so I'll import my encrypt and decrypt. And I will encode stuff because I need some valid ciphertext to start working from. So I import encrypt and decrypt, and then I encrypt that message. So this mess here, starting with 98, that is the encrypted version of this simple sentence is 47 bytes long. All right. Now, I'm going to put that in C. It's in the variable C. And I can decrypt it and look at it in hex. If I decrypt it, I see exactly what I expected to see. But if I decrypt it, but there's a character missing. If I put it in hex, you'll see it's got that 0, 1 of padding at the end, which did not print because it's not printable. So really, this ASCII printout didn't tell me the whole story. It does have 1 at the end, 1 byte of padding. So now we can observe the vulnerability. If I modify the input by just changing the last character of the ciphertext, so I'll take the first 47 bytes the way they are, and then I'm going to add a 65, a capital A, just as an arbitrary change. When I decrypt that, it's going to tell me padding error. Now, that is the kiss of death. Just like when you put an apostrophe and you see a SQL injection error, you know you can take over that server. When you see this, you know you can crack this encryption. Because since it tells me the difference between good padding and bad padding, I can modify it. So what I want to do is create a valid encryption message that ends with the word win. And here's how you do it. You don't attempt to find the key. You attempt to find this intermediate state. After the input comes in, I'm never going to change the last byte. So the byte comes in, and I'm going to let it encrypt and form something here, and I'm never going to mess with that. So this intermediate state is always the same, and I'm going to find out what's there. I'm going to find out by messing with this one. If I change that byte, that's going to destroy all of this and change only the last byte there. Now, the original correct valid message had some padding at the end of an unknown amount. It might say 7 bytes of padding. But if I change all the gray bytes there into just junk, then I will scramble this stuff so the padding won't be valid anymore. And I'm going to bury it until this turns into 1. So this is the game. You start with valid ciphertext. You replace all of this with junk. Then you vary the last byte until the padding is valid. And now you know that this number is 1, because that's the only way it can be valid. So you know this number is the one that didn't create the error. You know this one is 1, and when you XOR them together, you find that orange value. And you can then find this one and this one and this one. And with only a small number of computations, you can totally control the last block of data. And you can then repeat it and go back and back to the left until you get everything except, I think, the first block you can't get this way. So we need to get valid ciphertext. So here this sentence clearly says I'm a loser, and I'm going to encrypt that. That's going to be my starting text. So there it is. And I'm going to call it original. So I've got it to play with. Now, I want to find that intermediate value 47 right there. So to find it, I just have to try some modifications. Let's first just try putting 5 modifications there. I'm going to make my modified text original 31 plus character I plus original 32. I'm just changing that 1 byte. And if I do that, they're all just padding error because only 1 of the 256 guesses will be right, and it didn't happen to hit it yet. So let's just carry on this way. Should I show you the whole story? I'm going to just go through all 256 in that 1 value and only change that 1 value. So now I made it so it only prints out the correct ones, and there are 2 correct ones. The reason there are 2 correct ones, of course, is one of them is actually the original unaltered text with valid padding. And the other one is garbled text with a 1 at the end. So there are 2 answers. So you could now just go look and see which one of these is the current value, and you know the other one is the padding. But what's simpler is to just mess it up. Just fill it all with capital A's. It'll totally mess it up. And now there will only be 1 valid decryption result, and it'll be the right one. So here I knew there's 147 or 154. And if I just do it this way, where I take the original byte, next byte of all junk, and change that 1 byte until it works, I'm going to find out which one is actually right. And it's 147. So 147 is that intermediate value. Does that make sense? People look a little dazed. So that's how you do it. Then you just do it again to that next byte. Now that you know that that one is 147, you know how to get a 02 in there. The 147 here. Let me go back to my picture. I found out that when I put a 147 here, I get a 1 there. So I get a 1 there. So this number is 146, 147 or 1. And I can keep track of them. And all right, we're still with A's in it. All right, that's what happened here. So 147 is correctly padded. All right. 147 gives you 1. So here, I need to fill these with B's and try all 3256 possible values. Right, now this, I just did the same thing. I could use all B's instead of A's and I still get the same answer. It doesn't matter what junk I use. So now I know that this number is 147 when that number is 1. So I need XOR them together, and this orange value is 146. I've now learned 1 byte of this intermediate value. So if I want to get the next byte, I have to choose a different value here that will result in 2 there, and modify this one through all 256 values until I get another 2, and then it will be valid again. Because 2 bytes of 2 at the end is also valid. So I need to use 144 for ciphertext 31. That's the number that will create 2. And here's what you have. Now I have a bunch of B's, the one that's going to vary through 256 values, then 144, which will always create a 2, then the last block unmodified. And when I run through that, I'll get 6. So 6 XOR 2 is 4. So that value there is 4. And now I can chew my way back byte by byte until I can create bytes which when put here will spell out anything I want there. The cipher block chaining, which was trying to make up for the repetition property here, had an unexpected consequence that I can totally control this byte by messing with this one. And it happens after the decryption, so it has nothing to do with the key or the IV or anything. That's the game here. So I'm not going to dig through it because I see people sort of going to sleep on me. But here's the end result that encodes for win. You just have to find those values. Remember, we found the 146, we found the 4. You keep going and find these. And now you can carefully craft ciphertext that will decrypt to something you controlled. Take the original bytes the way they are, and you modify these 4 bytes to be calculated from win and have a 1 at the end to complete the padding. And now when you decrypt that, you're going to get a message that has win in it. Instead of saying, let's just saying, original message said you're a loser, and then had padding with H, but the new message has win in it. So, and I think you can actually accomplish even more with this if you get fancier, but that seems like good enough. So anyway, give it a shot. It's easy enough to follow along this way because I have the crayons, but then of course you have a challenge. So I gained another library you can download and put in where you don't have the key. This one you could look and find the key in the IV in the source code. This one goes up to my server where you can't see the key in the IV, and you can perform this attack. And what happens is you have to make, right now, it's going to decode to this string. Put this name on the winner's board, example. If you have a space there, it will not put the name on the winner's board. You have to put your name there. And when you do, you'll get there. Let me see if anybody's up there yet. Just me. All right. Well, you guys need to do, I recommend, you'll find it easier to make your name short. I had to do 5 bytes to do this. So I could have the colon, and then, I don't know why I needed 5, but I needed 5. I think something to do with the space. Anyway, it's doable. It'll put your name on the winner's page if you can make something that will decrypt with a colon followed by your name and have correct padding.
Colon, no space.
What's that?
Colon, no space.
No space. If there's a space after the colon, it will not print the message, so I could have my example, and people can practice with my example, and it won't fill up your board. Yeah, you got to get rid of the space.
So if it's padding is not
just one byte, then you're looking for a different?
Well, you could have more bytes of padding, but it would just be more work for nothing. You know,
Right.
like what I did here, the original thing was short and actually had 8 bytes of padding. And I didn't want to work hard, so I just put 1 at the end and then my chosen text here. I could have wiped all that out, but I just have to keep doing it more times to dig my way back. But you are going to have to dig your way back, I think, to the colon anyway. Maybe not. I forget. The colon, I think I made it so the colon's in this block that you're destroying. So you can put, that's why it takes 5 bytes. I put in a colon and then my name and then the 1. So for a 3-letter name, it took 5 bytes. And that I think is pretty much the minimum, unless you can shrink your name down to 2 or 1 letter. Yeah.
What's the maximum?
The maximum, I think, is you can get all of it. You can do block after block right back to the first block with this attack. And then the first block you can't get.
So you can change everything but the first letter to whatever you want.
You can change everything, but maybe the first 16 letters. I think inside the first block, you've got a problem because there's no block before it to modify. So this attack doesn't get you everything, but it gets you a lot. And there are some tools people made, and they talk about having some kind of brute force attempt to get the first block, but I don't think it'll ever work with AES. But I think you can actually do even more with this. There are more advanced versions of the attack. But this part is pretty awesome. It's enough to totally manipulate web requests. And there are similar ones. There are quite a lot of encryption attacks in the Web Application Hacker's Handbook that involve not decrypting the text. Like another one is pretty cool. If they use ECB, you can just take blocks of ciphertext and move them around, shuffle them. So now ID equals 173 will turn into ID equals 1 and turn you into root. And the dollar amount will have a few digits from this block and a few digits from that block and might be totally different. You know, you might have garbage, but you might just get lucky. And just by reshuffling blocks of letters, it might add up to interesting parameters that do things. There's a bunch of these things where the original designers of the crypto system may not have thought of ways you can abuse it in practice. Actually getting the key and breaking it is always the hardest because that's what the designers are really thinking of, is someone's going to try to find the key. So they've usually really made that hard. But there are ways to exploit it without finding a key.
Something hackers book.
The Web Application Hacker's Handbook. Yeah, we have a class here. That's 129S. I don't think it's next semester, but it might be the semester after. It is next semester. Yeah, we'll be going through that.
Okay.
Yeah, it's fun stuff. Attacking encryption without decrypting it. All right. Any questions or anything? Oh, well, somebody should tell me who Buster is. If you're online, tell me who you are. Aha, here comes a name. That might be telling me, oh, good. Good, thanks. Okay, I found out who Buster is. Okay, well, I think I'm going to shut it down and I'll go to the lab. I will be about 20 minutes before I get to the lab. I have to go do an evaluation of another teacher.
Go easy.